Regional. And I actually, weirdly enough, the yeah, the map should open, right? What did I didn't understand. Sorry, that was like, oh, did you hit the? I said bash? No. Yeah. Headbutt. The door is strong enough. Proprio un dondolone comunque.
Sì, anche perché lo cercavo, ma stava lui da davanti.
Dondolone.
Andiamo, vediamo, non c'è nessuna cosa per metterci in pari.
Sembra, c'è presente i film di Harry Potter, Peter Miller, quello che poi si trasforma in un topo.
Sì. Yeah.
It was great. Thank you. Not so much, but he's in the other cover at CGD. I see. Or small fields. Oh, that's. Oh, yeah, because there's something just that.
Put them out. Cleaning. Yeah.
So I'm having a problem with the charger of my computer. Yeah. So just plug it in. Let's see if it's charged. Okay, yes, now it is charging.
Okay.
We are starting at 1.
1 o'clock. Yeah, 10 minutes. Do I want to? Hey.
Yeah.
You bought your phone one?
No, I was okay. What's it behind you guys?
Oh. Oh, that's cool. It looks like paper.
Oh yeah, it's a Kindle Scribe.
Haha.
So it feels like you're writing on
A
paper.
paper, really?
Yeah. So it feels just like writing on a notebook almost.
Can I feel it?
Yeah. But I take notes on stuff all the time for different stuff. And
Oh, wow,
it feels-
that's so nice. Yeah.
it's easier to
How are you reading? Oh.
yeah, it's good.
Wait. That's cool.
Yeah. It's easier than a paper notebook.
Right.
It's a Scribe Kindle too, so I can take it with me and like read a book or a paper.
I have a Kindle, but I don't have one that I can write.
Yeah.
It does feel like writing on paper.
Yeah.
It feels nice. It's on the legit papers.
Yeah, exactly. You never run out. But it's nice too, yeah, because it's still a Kindle, so you can like,
Go back and read.
yeah, you can read books on it the same way.
Is this supposed to be better for your eyes than reading on iPad?
Yeah. It's like, the Kindle, how they're very soft
Okay.
to read on, so, and then the
Distracted.
battery lasts forever.
Yeah.
It's hard, I don't know, it's hard to see.
Oh. Okay, cool. It's a advanced version of Kindle.
I will, kind of.
Okay.
They actually just came out with a color version of it. This is black and white.
Which is now full.
It'll work.
You could change, you
She thought we would need some Christianity. Me too. I show you the.
How can I join the Google Meet?
Oh, do you
Yeah.
They send email every morning.
Might have been the second one down. Because there was 3 different links on there to the 3 different.
Yeah, eventually, we're all together. He's trying to hide all the people.
Maybe it is.
The first one is from Mo.
Yeah. I think I was.
Yeah. No. This weather event. And a lot of them, right, the airlines are being up again. There's only one we can. The most famous one is there was a really big Europe. Yeah, over in Europe. So many. Joe, that did not finish that.
You didn't go to AMS, right? Yeah, we had the time at all.
Everybody just sent an email she wants to.
Yeah.
This week.
So here mostly, here's
They just make it on me. Sometimes I do that, like I just batch all my meetings on one day, trying to get 5 done in between. Challenge anyway.
however, they tell us shifting part of our work. That means that there is a better relationship with Canada and we want to keep yeah. Yeah, so ultimately Well, it's difficult. But, all of this, all of it kind of overlapping. Every year it happens. Because everyone knows something.
I'm thinking we should be like BAAWG, chemistry and Emerson.
Well,
Just-
trees are.
It should be. Yeah. Ring Oh.
So is the mic already open for people?
Probably. I think so. Yeah, I didn't turn it off.
I think you can share us.
So, yeah.
Hi, Alwa. Are you there?
Hi.
Excellent. So we'll wait a few minutes until
Okay.
people go lunch. If you would like to start sharing your presentation, you should be able to do so. And we'll wait a few minutes just before we start. Okay, thanks.
You can run on, the problem is, you just, you cannot switch it to different. Because it's thinking, I just, but in NPI, you can be incredible.
If you have a badge, you can get to get back to the completion also like. Oh. I come from, where do you go?
It's right.
Opinion for it.
We can see the presentation that there is this other screen covering the part of the.
I don't know. I don't know how. Because I see two screens here too. I don't know if it's okay.
You can close that. Go ahead.
Oh, is it closed now?
Yeah. Perfect. Okay, let's wait one more minute.
Okay.
Okay, should we begin? So welcome back, everyone. My name is Rafael Fernandez. I'm the external co-chair of the Chemistry and Aerosols Working Group. That's the name we have now. And I will be chairing the last part of the session of lunch. So next speaker is Alwa. We'll be talking about quantifying the changing role of natural aerosols in the field's air quality and carbon impact. Go ahead.
Yeah. Hi, everyone. Thank you for the opportunity to present today. My name is Ajoa Abuaji Ochere. I am a PhD candidate working with the Mahoward Aerosol Group in Cornell University. In this talk, I'm going to show you how we are using CSM Musica to examine the changing role of natural aerosols, especially wildfires and dust, and how they shape PM2.5 exposure and health impact across Latin America with a high resolution over Brazil. Okay, so first off, I'm going to talk about wildfires in Brazil. So this figure here is just showing us, it's a figure from CAMS, and it shows wildfire carbon emissions for 3 Brazilian states, the Mato Grosso, Amazonas, and also Mato Grosso do Sul. So if you look at the top panels, the gray lines show cumulative emissions for individual years between 2003 and 2023. And the black line is the historical mean, and the red line we see is 2024 wildfire carbon emissions. So what stands out is how early and how rapidly emissions increased in 2024, especially over the Amazonas and also the Mato Grosso. And you see by late August and September, emissions are already well above the historical mean and among the highest in the record, even before the fire season ends. And so this extreme wildfire dust and event increasingly affects this Brazil's air quality. And somewhere in 2024, there was a wildfire emissions in Brazil that spread to neighboring countries. And during this event, it increased hospitalizations for different diseases. So more exposure to PM2.5 over Brazil increases the risk of health impact and also premature mortality. And when we look at Latin America in terms of air quality studies, it's poorly quantified, and also high resolution scale consistent modeling is needed to be able to understand how these wildfires in Brazil and Latin America impact air quality and also impact pre-SS mature mortality. So given this large scale fires, this study is framed around 3 main questions. So our first question is, how do wildfire and dust emissions influence PM2.5 exposure across Brazil? And a second question is, how does the population distribution shape PM2.5 attributable mortality? And how does the Musica improve exposure estimate relative to using a COSA global model simulation? So this schematic is showing us the study area, and also we are doing a high resolution over Brazil area, which is in blue here. And so to our modeling framework, so in this work, we are using the Musica in CSM, and it's basically just the multi-scale chemistry aerosol modeling framework. And that let us study air quality consistently from the regional scale to the global scale, all within the CSM. And so in this our study, we are having the high resolution, which is like 14 kilometers all over Brazil. And so even though all the simulations are global, our analysis focuses on this particular area in Brazil, where we examine exposure and impact at a final spatial scale. And this is very important because Brazil spans regions with very different emission regimes, meteorology and population density, and from the Amazon to the major urban centers, all within the southeast. And the key feature in this study is that we are using a high resolution over Brazil, and to the best of our knowledge, nobody has. This is the first study that is doing high resolution using Musica over Brazil. And for our emission data set, we use the CAMS for our anthropogenic and also biomass burning from FIN 2.5. And then this setup is particularly well suited for aerosols like smoke and dust, where long-range transport plays a very important role in determining surface PM2.5 exposure. So here we just present the preliminary results from the model run that we had for PM2.5 over Brazil. So on the left panel here, we see that the background shows the model PM2.5, and the dots here are just indicating observational sites in Sao Paulo. So we wanted to test our model performance with surface observations over Brazil, and we found some stations in Sao Paulo that had surface PM2.5 observations. And so we tried to match our model to understand how well this model is doing in terms of PM 2.5 exposure over Brazil. And then we see that the highest model of PM 2.5 occurs in the fire-affected regions of central Brazil, which we all know of. And then urban pollution in Sao Paulo is seen in this also in this plot. And the one thing that actually stands out is the fact that the model was able to capture the spatial patterns of PM 2.5 over Brazil, but in terms of its magnitude, it really underestimates PM 2.5 because for annual observations for just 1 year, so that's just 1 year simulation for present day for 2013. And then we see that the observations for 1 year is about 18.75 microgram per meter cube, but our model is annual mean is around 12.59. And then when we estimate the model at the observation site, we have about 13.78 microgram per meter cube. And then even though there are these biases.
Excuse me, can you please hide the Google Meet bar?
Sorry?
The small bar on the bottom.
Yeah.
Yeah.
Yeah. Oops, sorry. Oops.
Oh.
Oh. Oops. Oh, let me stop. Sorry, let me share again. Thank you. Where is the Google Meet? Okay.
You just have to go back to the other screen. You need to stop sharing.
Oops. Okay. Let's close this. I don't know if I close. Oops.
Let's go to your PowerPoint.
Yeah. Yes.
That's great. Thank you. Sorry.
Thank you. And so here we just present the preliminary results of PM 2.5 estimate. We use the CSM Musica over Brazil. And one of our main focus of this work is to assess the health impact. So we're using this preliminary model outputs for PM 2.5 over Brazil to estimate how many people are dying from prematurely being exposed to PM 2.5 from over Brazil region. So to be able to get this to it, we have the health impact framework. So we use the health impact framework to estimate how much people are dying prematurely from being exposed to PM 2.5. So this equation basically helps us to calculate premature excess mortality from PM 2.5 exposure. So we use the population of the exposed area, the baseline mortality, and also the attributable fraction of the population exposed. And so we're able to establish the concentration response relationship between particulate matter exposure and premature mortality. And so in our estimate, we try to use this framework to estimate mortality from different cause-specific mortality. So we are not doing all-cause mortality. So we are estimating premature mortality for 6 specific disease groups. So people who are exposed to stroke, heart disease, COPD, lung cancer, and lower respiratory infections, how much are they dying prematurely from being exposed to PM 2.5 while having these underlying conditions? And so one thing to note is that mortality is estimated as a function of PM 2.5 concentration, baseline mortality rate, and population. And so we're able to calculate how many people are dying prematurely from PM 2.5. So I'm going to show quickly, this map is showing us the PM 2.5 attributable mortality over Brazil. And then this plot here is showing us the different diseases and how it impacts mortality over Brazil and also Latin America as a whole. So we saw that the mortality hotspots are concentrated in the southern Brazil. So we see that even though the concentrations we are seeing here, most of the concentrations are over the Amazonian regions, but in terms of mortality, because there are not many people living over these areas, and so mortality is concentrated on where people are living. That's why the Amazon regions are showing low mortality despite having the highest PM 2.5. And then the spatial pattern of this mortality is more population weighted than PM 2.5 weighted. And so if you look at this various diseases, we see that lower respiratory disease affects people die prematurely from lower respiratory diseases and then being exposed to PM 2.5 compared to all of the other diseases that we have over here. And so in summary, we're able to see that this Musica with the 40-kilometer resolution over Brazil is able to produce the major PM 2.5 spatial patterns across Brazil and Latin America. And the high resolution modeling we are using helps us to improve exposure estimates in a densely populated region, even though it underestimates PM 2.5. And also, mortality is highest in urban regions where pollution and population overlap. So since this is an ongoing project, so our next step, since we talked about PM 2.5 from dust and wildfire, so our next is to isolate biomass burning contributions and then quantify its specific role of fires in terms of PM 2.5 levels and mortality burdens, and also make a future projection over PM 2.5 over Latin America and Brazil to know how PM 2.5 concentration will change in future under different climate scenarios. And our next step is also evaluate the economic impact of PM 2.5 exposure, including productivity loss and how much money is lost to the economy when people die prematurely from being exposed to PM 2.5. And the next step is to be able to add more observational constraints to be able to fine-tune our model to make sure that we are matching the model close to observations. And I'd like to acknowledge the following people who are my working collaborators, my advisor and other collaborators, also with support from the Cornell Atkinson Center for Sustainability, Environmental Defense Fund, and also the computing resources from NCAR and Derecho. And that's it for my talk. Thank you.
Excellent. So thank you, Edward, for making on time. So is there any question? I do have a question or a comment for you. So I'm aware that sometimes CAMs underestimate pollutant emissions in Latin America in particular. I'm not that familiarized with Brazil, but there is a project called Papila. They develop an emission inventory of different gases and aerosols. Have you thought about comparing with those emissions?
No, I haven't yet. So we are yet to meet with some people in Brazil to give us like surface observational data set. And so this is very new to me. So thank you very much. Could you mention the name of the network again so I can just take a look at?
Yes, I'm just copying the link on the chat.
Okay. Thank you very much, because we are trying to. So right now, the anthropogenic, when we look at the global PM 2.5, we see that we're not getting the signal from China as much as we could get if you are using the CMIPS emissions. So we are trying to better match those observations in this area.
Okay, thank you very much.
Thank you.
So is any other question?
Just comment. It's great to see Musica applied to yet another region, another custom grid. So that's great. Thank you.
Thank you.
Yeah.
I noticed you looked at mortality.
Yes.
Are you thinking about looking at morbidity as well, like just disease increases?
Yeah, it's one of the things we want to also look at in terms of that. We use that one to help us calculate the productivity losses in terms of PM 2.5 exposure. So yeah, we would look at the mobility from PM 2.5, which will help us do the productivity losses.
Okay, thank you.
Excellent. Okay, thank you very much. Can I stop sharing the screen? So next speaker is Jun Zhang. He's presenting here about the improved representation of aerosol photolysis interactions using TUVX and implementation in CSM. So,
okay. I'm doing everyone else, and today I will present the improved representation of aerosol photolysis interactions in CSM using inline UVX. Then I will use Pinatubo as the test case to see how much the inline UV changes the ozone loss, and to look at the impact on surface UV. I would like to acknowledge all my colleagues, especially Del Kennison. He was able to lay all the important groundwork before he retired, so I can step in and carry on this work. It makes my life so much easier. And also, I really want to acknowledge Francis for all his help. Every time I go log on his door, go like, Francis, and he knows I have a problem. Always willing to help. Really appreciate that. Okay, so to start, we know that the solar radiation in the atmosphere doesn't travel in a straight line, and it gets absorbed, scattered, or reflected from aerosols, clouds, and molecules. And those processes can affect the photolysis in the atmosphere. And we know that the photolysis process play a key role in atmospheric fluid chemistry. It initiates important cycles of the chemical composition change, both in the mid-atmosphere and in the tropics. I mean, the troposphere. And so proper representation of all those processes are critical in our model. But here in my talk, I will be only focused on the aerosol photolysis reactions. In CSM Wacom, we calculate the photolysis coefficients J based on the cross-section and quantum yield, and also the top of the atmosphere, the incident wavelength-dependent radiation. It is modified by the Earth's distance and the 11-year solar cycle. And the key term here is influx, which is in atmosphere flux after attenuation. It's a function of pressure, column ozone, solar zenith angle, albedo, and aerosol and clouds. So in our current model, we use the lookup table scheme, and I will call it LUT scheme. And it's an offline calculation of influx using a photolysis calculator TUV, which is based on the Sasha's offline TUV model. And it assumes a fixed mid-latitude ozone vertical profile, and the photolysis rates scaled by total column ozone. And the aerosol effects are not included in this old approach. So it used the pre-calculated lookup table, and so there's no feedback from chemistry or dynamics. And now we have this inline TUV scheme in the CSM, where it calculates the influx inline within CSM. So it used real-time modeled ozone vertical profiles. So the photolysis rates respond dynamically to evolving atmospheric states. And it also, the new feature explicitly account for the aerosol optical properties and fully coupled with model chemistry and aerosols. So currently in our CSM model, we are able to consider the aerosol photolysis interaction of sulfate, secondary organic aerosol, dust, sea salt, primary organic matter, and black carbon. We take the extinction optic depth, signal scattering albedo, and symmetry parameters of those aerosols and feed into the TUV to calculate the photolysis rate, then feed back to the CAM. That's the workflow. We are able to calculate other aerosols too, if our model includes those aerosols in the future. In addition to the aerosol photolysis interaction, now with inline TUV, CSM are capable to compute a comprehensive suite of biologically active dose rates, which fully coupled to ozone and aerosols. It can calculate spectrum, board bands, irradiations, irradiance, such as UVA, UVB as visibles, and photosynthetically activate radiation. And it also able to use those irradiance to calculate more socially relevant variables like the DNA damage and plant damage growth, and the human erythema, UV index, and so on. All those calculations are based on the previous references that I didn't list here, but I can show it in the code if you need. So now we have this new configuration, and then I'm using the Pinatubo as a test case. Here I did 4 simulations where I used 2 different photolysis scheme, lookup table and TUV, and in both scheme I did a control case where there's no Pinatubo injection, and the experiment case where it has Pinatubo injection, and all those simulations have the same initial conditions, are not the same dynamics. So the differences are attributed to the photolysis scheme or with and without Pinatubo injection.
Just go back to your PowerPoint.
Yeah. There we go. First we validate the aerosols before we look at the aerosol photolysis interactions. Here it shows the lookup table simulations and TUV simulation comparison to the 2 observation datasets, GLOSAC and AVHRR. You can see that the model simulations actually compare pretty well with the both observations, and the TUV and lookup table has consistent AOD. So if we see any difference, it's not from the aerosol representation in the model. Then we're looking at the total column ozone. Here I'm showing the total column ozone across 3 regions, South Cap, near global, and the Northern Cap. Compare against SUVB satellite data. Here the orange and blue lines are the TUV and lookup table, and the x-axis is 3-year time series. And you can see that the inline TUVs reproduce observed magnitude and seasonal evolutions of column ozone better than lookup table across all the regions. Okay. So that was the total column ozone. Here we're looking at the ozone vertical profile in both simulation, and now we're only looking at the summer months in 1992 July. 3 panel also shows the 3 different regions, and again the orange and blue. The orange and blue are the results from the TUV and lookup table, and the gray dashed line is the aerosol layers. And you can see that TUV has higher ozone concentrations above the aerosol layer compared to the lookup table. Then I dig deeper to see why is that. Here it shows the net odd oxygen, which is the total production and total loss, which controls the ozone concentration up there. So it shows that the TUV has relative higher net odd oxygen across all 3 regions. That's why the TUV has higher oxygen, not oxygen, ozone there. And we see that the aerosol photolysis interactions dampens the net ozone depletion compared to the lookup table in the polar regions, and enhance the ozone production over the near global region. Okay, here we're looking at the total column ozone change induced by the Pinatubo injection. So it's calculated by the difference with and without Pinatubo injection. And we see that the aerosol photolysis interactions can modulate the volcanic induced ozone loss for all the regions. And it's reduced the ozone depletion in the southern polar region. So it's like 5 DU differences in some months. And all those differences we see across all three regions could be due to that the TUV computes photolysis rates using the involving ozone rather than the prescribed middle latitude ozone and the aerosol fields. So the volcanic aerosol directly perturb the vertical distribution of actinic flux and ozone chemistry. Okay, here it shows the Pinatubo-induced total column ozone, the top, and the UV index change, the bottom. Immediately we see that there is a high UV index change corresponds to the high ozone loss. And the strong effects are at northern hemisphere and southern hemisphere, mid to high latitudes during summer months. And the E-night UV simulation indicates the Pinatubo eruption increased the global UV index by up to 10% at high latitudes during summer 1992. Then we want to take advantage of the model now directly outputs the socially relevant variables. Here we're looking at the July 1992 total column ozone change. The blue dashed line shows where the reduction is higher than 5%. And we can also see the corresponding increase in risk in erythema by more than 5%, and the DNA damage by 10%, even more than Europe and Canada region. Okay, in summary, the inline UVX photolysis scheme has been successfully implemented in CSM, enabling fully coupled online calculations of photolysis rates that responds to real-time changes in ozone and aerosols. With inline UVX, CSM can directly compute biologically active ultraviolet radiation, including diagnostics relevant to ecosystems and human health. And a Pinatubo case study demonstrate that aerosol photolysis interaction can modulate volcanic ozone loss, resulting in reduced ozone depletion in southern polar region. And the E9 UV simulation indicates that the Pinatubo eruption increased the global UV index by up to 10% at high latitudes during summer 1992, and also increased risk in DNA damage and erythema. And this study shows that proper representation of aerosol photolysis interaction is very critical for other applications, including air quality studies, because of the radiative dimming below aerosol layers. Previous study has shown that that would reduce the surface ozone, and maybe the strategic aerosol injection assessment too. Okay, thank you. That's what I have. I'm really sorry for the pop-ups. It's very distracting. Even for me, I forgot what I did there.
Thank you very much, June. So we have a question, Daniel.
Yeah, thank you, Jim. This is great. You almost always showed total ozone column, but it would be curious to see tropospheric ozone column and surface ozone. How does that change? Because when you then show the changes in exposure in UV, it would be interesting to see also then how air quality due to surface ozone changes. I would expect there to be a stronger feedback on surface ozone in that case. So have you looked at these or?
No, I actually didn't look at that. But it would be interesting because here I had the Pinatubo injection. For the surface ozone, I would expect even it's not Pinatubo, you would see differences too, because the aerosols from the city area. So.
Right, but then you're going to have a feedback with the actinic flux, right? If you're changing
right.
your
Yes, you're right.
and the cooling from Pinatubo. So just curious to see what the impact would be on surface ozone, if there is any. Maybe there isn't really any because of all the other reasons.
Yes. Okay. Yeah.
Yeah.
Yeah, I have a quick clarifying question. Did you notch the temperature and wind field both to the control and Pinatubo cases to the same?
Yes. Yes.
I was wondering whether if you notch temperature field both in control and Pinatubo, then might underestimate the ozone change because temperature relatively reflect the Pinatubo case, and have you consider like not just wind, not temperature, or just fluid?
Yeah, that's a good point. Here, no, we didn't consider the dynamical change because we matched to the same parameters. But yeah, Timon, we talked about doing free running simulations, but here we mostly just look at the chemical changes from changing the photolysis rates and from the change in actinic flux with errors.
Great. So I also have a couple of questions, but I can ask you later. So
Yeah, sure. You listened to it twice already, Rafa.
Thank you very much. So next speaker is Jesse Miller. If you would like to share your screen, we'll be talking about atmospheric and climatological responses to past encounters with dense interstellar clouds.
All right, hello, can you see my screen?
Perfectly, yeah. Go ahead.
All right, great. So my name is Jesse. I'm here to talk about something very exciting at the intersection of astronomy and climate science. So my background is in astronomy. In grad school, I was studying supernovae. And so in my postdoc now, I've taken this hard turn into atmospheric and climate science. And I decided to thank all of my collaborators here who have helped me with that transition. All right, so the motivation for this is that when you look out at the galaxy, you'll see that there are lots of these very dense clouds out there. And over 1 million year timescales, stars are not static, they move around in their environment. And sometimes we can go through these very dense clouds. So as a little animation of what that could look like, here's the sun, the extent of the solar wind, not quite to scale here, but going through a very dense cloud pushes on the solar winds, which we call the heliosphere. If that cloud is dense enough, it's going to compress the heliosphere so much that now Earth is no longer protected by its shape. So Earth is totally exposed to this interstellar cloud and the rest of the galaxy. We'd get a lot more cosmic rays, a lot more interstellar dust, and many other things would be going on. I don't want to talk too much, but by pointing telescopes in the direction that our solar system came from, we can see areas where there are dense clouds in this path, areas where we could have crossed these dense clouds. So I'm happy to go into more detail on this, but for now, please just take my word for it. There are these potential crossings that could have happened a few million years ago. So one around 2 million years ago, one around 7 million years ago. This upper plot here shows something similar to the animation, but just a more scientific version, the full magnetohydrodynamics model of the heliosphere. And in this red circle here, this is Earth's orbit. So this is showing that for most of the year, we are exposed to the interstellar clouds. So what does this mean for our atmosphere? Well, several people have looked at this, kind of played around with it throughout the decade. One approach that I liked was by Chris McKay and Gary Thomas back in the late 70s. They said that all of this hydrogen coming in from the interstellar cloud is going to hit the upper atmosphere. There will be a series of chemical reactions that will end up with the production of very high altitude water. And that could lead to what they called at the time mesospheric ice clouds. Today we would call them polar mesospheric clouds, PMCs. So with a different model, I was looking at this. This was with a 2D Goddard model. I was looking at the production of these PMCs. McKay and Thomas had suggested that you would have so much water that you would never get rid of these polar mesospheric clouds. They would be completely global in coverage, and they would last the entire year. But I've been showing that that probably isn't the case. Nonetheless, there are some other effects that we could look at. So along with the generation of this high altitude water, we can ask, how does that water affect the climate? So for most of the year, over most of the globe, the water is just going to hang out around this high altitude. But what's more exciting is when it gets brought down to lower altitudes. So very briefly, here's the simulation setup. This is akin to an FWMA 1850 CompSet. I know that the atmosphere was different a few million years ago rather than pre-industrial, but let's take things one step at a time here. So to simulate going through this interstellar cloud, the process is relatively straightforward. I've just added a source term for water at around 70 to 80 kilometers that is global and constant in scope. So the amount of water I'm adding is dependent on the dynamics of this interstellar cloud. What is the density? What velocity is it hitting us? In the end, this comes out to about 30 teragrams per year of water into the upper atmosphere. So the first thing you might want to know is, how much water is this compared to the rest of the water in the atmosphere? So this is showing the total water burden. Here I have the control in blue and this interstellar cloud forcing in orange here. And this is 120 years of the simulation. So there's a bit of startup time, maybe five years or so, to reach some kind of equilibrium. But then it maintains this persistent 10% increase in the global water burden. So this is about 100 teragrams. And for comparison, the Hunga Tonga eruption injected 150 teragrams of water into the stratosphere. Of course, this case is very different. Here, we're not looking at a single instance of injecting water over the course of a few hours. This is a persistent thing over a century-long time scale. All right, so like I said, most of the water hangs up around the upper atmosphere and doesn't go anywhere. But what's interesting is when it is brought lower into the atmosphere. So here we're looking at the first 3 years of the simulation. This is altitude time. So we're looking to control what happens. Oh, this is also over Antarctica, by the way. So this is looking at how or what happens as the polar vortex forms. So usually the upper atmosphere at 80, 100 meters is very dry. So during the formation of the polar vortex, it brings down very dry air. But now we have very, very moist air because of this source of water caused by the interstellar cloud. And this polar vortex is going to bring down the very moist air down well into the stratosphere. So we end up getting an increase of water even below 30 kilometers. And that's particularly interesting because here, this is this black dashed line, these are temperature contours of 188 Kelvin. That's about the temperature threshold that you need for polar stratospheric clouds to form. And you can see we're bringing down enough water to just kind of skirt that upper edge of where the PSCs are. So the next step is to look at these PSCs and see, are we really seeing an increase in the amount of PSCs? So now we're looking at altitude latitude plots here in the control and the case and difference between them. So just by eye, between these two plots on the left, you can kind of see there's a bit of an increase in the amount of polar stratospheric clouds. Taking the difference between them, that increase is much more obvious. This half region is the result of a t-test that is statistically significant. So yeah, the differences are indeed statistically significant as we would expect. What we didn't expect, though, was these changes that we're seeing further down in the atmosphere, in the troposphere. So here we're seeing this strange decrease in the amount of ice around 5 to 10 kilometers, and then an increase below around 2 to 3 kilometers. And at the moment, I'm still scratching my head over that. So if you have ideas for what's going on there, then I am certainly open to suggestions. Another way we get the PSCs is now looking at altitude time. So we can look at the seasonality of the PSCs. And with these red dashed lines to kind of guide the eye, we see that the PSEs start a little bit earlier and they last a little bit longer. So the takeaway from this is that with this increase of water brought from this interstellar cloud, the polar stratospheric clouds are extended in just about every direction. They're greater density, they reach higher altitudes, they're brought down to greater latitudes and an extended seasonality to them as well. All right, so I'll wrap things up here just by saying that passing through these interstellar clouds that we think happens multiple times in the past few million years, that can alter the atmosphere. The next step is how can they alter not just the atmosphere as a snapshot, but climate in general. So the mechanism for that, the best mechanism we think is bringing down high altitude water from the polar vortex. That's going to enhance the production of polar stratosphere. And these PSCs are known to have radiative effects on the surface. So the next step that I'll be looking into is what are these radiative effects that we can see? So there are many other ways that interstellar clouds can affect the atmosphere through increased cosmic rays, more interstellar dust, but we're trying to take things one step at a time and go, step by step, to isolate the effects, and then we can bring it all together. So with that, I will end it there, and I'm happy to take any questions.
Any question for Jesse? Yep.
Thank you. Very interesting. Was there any substance temperature changing due to the water vapor radiative effect, and whether it also affected the PSC formation?
Right. So yes, I do have a slide on the effective temperature here. So most of the PSC formation is due to an increased amount of water. There is a temperature effect, though, and that is mostly confined to the mesosphere in general. There's a decrease of a few degrees up to about 4 or 5 degrees. But to get down further into the stratosphere where the PSCs form, there's not an enormous temperature difference there.
Thank you.
Yeah, I just have a follow-up question on the temperature response. So at the altitude of PMC, how much is the temperature change? Because my understanding is that PMC is very sensitive, even responding to plus or minus 1 to 2 K.
Yeah, that is something I don't have here. Maybe I should have extended this plot down a little bit further. But yeah, that's something I'm still looking into. I don't think there is an enormous decrease in temperature. 1 degree, maybe 2 would be reasonable, but certainly not 5 or 10 degrees.
Any other questions? Okay. Yes, thank you very much. So we'll move to
All right, thank you.
the next presentation that will also be remote. Lily Wu, modeling volcanic ash impacts of the 2010 eruption. Volcanic eruption.
Yes, hello. Let me pull up my, it's not letting me get PowerPoint on. Hold on 1 minute. Oh, sorry about that, guys. Okay, there we go. Alrighty. Hi, everybody. You guys can see my screen, right?
Yes.
Okay, awesome. Hi, my name is Lily. I am a second-year PhD student at Cornell University, and today I'm going to be talking about my project, Modeling Volcanic Ash Impacts of the 2010 Eyjafjallajökull Eruption. So coming back down to Earth. So why do we care about volcanic ash? We can see from this schematic here that there's a lot of important impacts. We can talk about the societal impacts on aviation and human health, but we can also talk about radiative impacts and also possible chemistry interactions with other volcanic emissions like sulfates. And then we can also talk about biogeochemistry, so looking at the land and the ocean. For this talk today, I'm going to focus on the radiative impacts from the volcanic ash and the ocean biogeochemistry. So despite the importance of volcanic ash, it was previously neglected in these large-scale global climate models like CESM in favor of other volcanic emissions like sulfate aerosols. And this is because ash particles are larger and assumed to be shorter-lived, so their impact is limited to smaller scales compared to sulfates. So really, the goal of this project is to incorporate a new volcanic ash tracer into CSM to simulate a volcanic eruption and analyze the volcanic ash impacts. And so to first simulate a volcano, we are using a case study. So you can see in this cool picture here, this is the 2010 Eyjafjallajökull eruption in Iceland. This explosive part of the eruption occurred on April 14th. And we also had 4 distinct eruptive phases with different ash chemistry. And this is also a really good case study to use because we have observations of the eruption, both from the emissions to constrain the inputs of the model, and then also the impact further away on Europe to help validate the model as well. So just very briefly talking about the model, I'm using CSM 2.1 and the Community Atmosphere Model, or CAM6. This includes the modal aerosol model, MAM4, so that has the accumulation, the Aiken, and the core size modes for the aerosols, and then also the mechanism of intermediate complexity for modeling iron, or MIMI. And so this is really useful for modeling the iron aerosols that come out of the volcanic ash. So to incorporate ash in the model, we are building upon the existing dust framework in the model. So we're assuming that ash behaves similarly to mineral dust. We currently have an extended dust model that carries 8 dust tracers, but a previous sensitivity study showed that you don't actually need all 8 to capture the radiative forcing of the dust. So we condense those into 4, and then we use the 4 remaining dust tracers as our new ash tracers. And so these are divided based on mineralogy from the Eyjafjallajökull eruption. So here this table just briefly shows how we're dividing each percentage of mass into the different tracers. So again, these are divided based on mineralogy, and then the percentage of mass will also vary in time depending on what eruptive phase the volcano is in. In addition to that, we also ran a bunch of sensitivity studies because some of these volcano parameters are poorly known. So these include the distribution of the ash and the plume height, the particle size distribution, and also the deposition velocity, or the shape. So the first 3 right here, the low, base, and the high, these are describing the plume height distribution. So for the low case, we're assuming a constant mass mixing ratio of the ash throughout the plume. For the base case, we're assuming 90% of the mass is in the top kilometer of the plume. And for the high case, we're assuming 100% of the mass is at the maximum plume height. We also ran some small cases. So these are concentrating more mass in the smaller accumulation aerosol size bin. And then also some depth cases, which are increasing the deposition velocity relative to the dust. So this is on the top panel right here. This is a visual representation of the sensitivity studies for the plume height I just talked about. So we have the altitude in kilometers here. And again, the green is the constant mixing ratio, or the low case. We have the base in orange, and then the high is in blue. So this is the vertical profile for one time slice. And this will vary in time depending on what the actual plume height is. So here we have a time series, and this is the altitude, and the blue color right here, and then the brown color here represents the eruptive mass from the volcano in teragrams as well. And so we can get these eruptive mass and plume height from remote sensing observations. So that's all of the inputs that we need for the model. So once we have all of that, throw everything into the model and simulate our volcanic eruption. So now I'll show some brief results. So here we have some results I have observations to compare to just understand how well the model is performing. So right now I'm showing the particulate matter. So the spatial plot, we can see Iceland is right here in the middle, and then Europe is further away. And these circles represent PM10 station observations from the AeroMap data set. And then the model is on the contours underneath. And then for panel B, we have the observations compared to the model for the constant mixing ratio or the low case. And then for panel C, we have all of the different sensitivity studies, and these are the Kendall's-Tau rank correlation coefficients. And then the purple right here represents a background case without any volcanic ash, just for comparison. And so for PM10, we're really trying to understand how well the model is capturing the long-range transport of the volcanic ash to Europe. And as we can see from panel C, the model is actually performing pretty poorly compared to the background case without any volcanic ash. And we think this is because of possible model spatial resolution issues. So this is really showing that the model's not capturing the long-range transport of the ash very well. We can also look at the soluble iron. So soluble iron in volcanic ash is really important for ocean biogeochemistry. So that's why we want to take a look at this as well. Here, if we look at the spatial plot, again, the model are the contours underneath, and then the circles represent our observations. And these are observations from the RRS Discovery research crews that happened to be in the area during the eruption. And so the researchers on board were able to collect iron concentration at the surface. So panel B shows that time series of those observations in black right here. And this is on a log scale, I should mention. And then the green, again, represents one of the model sensitivity runs. Panel C, again, shows all of the different sensitivity studies. This is the rank correlation coefficients. And again, purple is the background case without volcanic ash. And so again, we can see here that the model's performing relatively poorly compared to the background case without any ash. And so we think here, this is because, especially very close to the volcano, there might be some timing delays in the model. So when we kind of account for that timing delay, we see an improvement in the correlation coefficients. And so we just think that very close to the volcano, we're not capturing the volcanic ash because of that timing issue. So that's all. That's just a brief snapshot of some of the observations we have. But what about some other variables where we don't have observations, but are also really important for the climate and Earth system? So here we can look at showing the radiative forcing. So this is the total radiative forcing averaged over about a month. And this is the all sky. So this includes clouds in the radiative forcing calculations. So here, again, we have the spatial plot, and you can see the volcanic ash plume right there in the red. Panel B is the average local radiative forcing. So that's just the radiative forcing at the volcano location. And then panel C is showing the global average radiative forcing. So if we look at the global, it's pretty minimal. The volcanic ash doesn't have that much of an impact on the global radiative forcing. What's really more important is the local radiative forcing. So we can see here very strong, very positive radiative forcing. They're on the order of about 24 watts per square meter for all of the different sensitivity studies. So this suggests really strong warming, at least locally, from the volcanic ash. And then another interesting thing to point out is that here for the local radiative forcing, the all sky case is not very sensitive to the plume height, the particle size, or the deposition velocity. We can also take a look at the clear sky radiative forcing. So clear sky does not include clouds. So again, we have the spatial plot, the local forcing, and then the global forcing. So if we take a look at the global first, we can see it's also very minimal compared to the all sky case. So really the volcanic ash isn't, adding too much radiative forcing to the global radiative forcing. What's really more important and what we want to focus on is the local radiative forcing. And we can see here this stands out. These two cases, the small cases where we're putting more mass in the smaller accumulation size bin, we see very strong negative radiative forcing. So this suggests pretty strong cooling from the volcanic ash. And so this really shows that for the clear sky case without clouds, it's very sensitive to the particle size distribution. And then last result I'll show here, we're looking again at the soluble iron, but here I'm showing the soluble iron deposition averaged over the monthly eruptive period. And so again, soluble iron is really important for ocean biogeochemistry. So I kind of have a little blurb right here if you're interested in that. So here we're trying to ask how much more soluble iron did the volcanic ash add to the ocean ecosystem? And so this bar plot right here, the y-axis is X times more. So just how much more soluble iron relative to a background case without any volcanic ash. And so we can see from these numbers here that it's really a lot of soluble iron. We have like 20 times up to 40 times more soluble iron. And again, I have the numbers in gigagrams here. So just really a lot more soluble iron added to the ocean ecosystem from the volcanic ash. And again, this has a lot of important implications for ocean biogeochemistry. Okay, I think I'm on time. So just quickly wrapping up. I have a lot of conclusions here, but the two main key takeaways that I want to focus on is that the ash plume height distribution is more important for the sensitivity of the results compared to the particle size distribution or the deposition velocity, or the shape, I should say. And then the volcanic ash really added a lot more soluble iron to the ocean ecosystem over the North Atlantic compared to the background case without any volcanic ash. So again, this is really potentially important for ocean biogeochemistry and the phytoplankton and connections to the carbon cycle downstream. And then just overall, we need a lot more work to better model volcanic ash. Okay, thank you.
Thank you, Didi, for presentation. Is there any questions?
Yeah, nice talk. Nice talk. I wonder the strong positive and strong negative difference, and all clear sky and clouded sky scenario. Was the ash serving as IMP or CCN that is causing into so much difference for RF sign? Do you have a physical explanation for the very strong difference?
Yeah, I think so. I have, let's see. So here I have like the aerosol cloud interactions. So here we can see especially like there's pretty strong negative aerosol cloud interactions, at least for the small case right here. But I think it's also just really important, like the presence of clouds in the model, right? If since the ash is aloft, the vertical orientation of the ash really matters. So just where is it? Is it above the clouds, or is it like below the clouds? So that really matters, and that helps determine the sign for the radiative forcing as well.
This is winter time. Is that serving as mixed clouds IMP over there, or you don't really see the interaction between the ash and the clouds?
There's a little bit, like in one of the tracers we have separated feldspars for the IMP, so there's a little bit of like activation there, but I haven't looked in it too much, but there is there, yes.
Okay, thank you so much.
I have a technical question. So you said you used this, you map the 8 bins of dust, and you consider only 4 for ash. How is the removal, the washout, or the position of this each of these bins considered?
Sorry, can you rephrase that question? The washout, I'm sorry?
Yeah, how is the removal of each of these bins that you are considering? Like to understand the differences in the long range transport.
Oh, so like for like the dust, I think I understood your question. So like we're so taking the 8 original dust tracers and then we're kind of grouping them into 4. So we're still keeping all the dust, but we're just grouping them into 4. And then we're using the new 4 like free as our new ash tracers. So we're still keeping everything like in the dust. Okay. Is that your question?
Okay. Thank you.
Yeah.
Okay. Okay, thank you very much. So we'll move to the next one, 2. So submissions will be presented consistent responses of Northern Hemisphere wintertime circulation to stratospheric injection.
Hi everyone, my name is Shin Yu. I'm a postdoc at MIT. There has been some apparent changes in the pattern of my talk. So today, I'm not just going to talk about the stratospheric fluid injection, but I'm going to talk about this in a context of nuclear war, which is quite a depressing topic to think about, but it is scientifically really a good framework to understand the impact of large-scale stratospheric aerosol injection on the climate. Can I? Okay. There's a delay. Okay. Sorry. So following the previous studies on India-Pakistan scenario, I focused on the regional war scenario. And it has been predicted that if India and Pakistan use their nuclear weapon to each other's cities, then it will ignite large-scale urban fires, and those fires will are projected to inject about 5 teragrams of black carbon into the atmosphere. So one of the major environmental impacts of this nuclear war scenario is its potential to deplete the stratospheric ozone. And Wacom for this India-Pakistan scenario predict about 80% of total carbon ozone loss over northern hemisphere, not just southern hemisphere, primarily due to the halogen and heterogeneous chemistry. And for those of you who are interested in more details, please refer to the paper just published in Earth Future last month. But today, I am going to focus more on the dynamical response to this nuclear war. So whenever we simulate the stratospheric aerosol injection in a different context of explosive volcanic eruption or geoengineering nuclear wars, regardless of if it's a surface aerosol or black carbon, we can see the aerosol into the heating in the lower stratosphere. And in following winter, we always have seen the strengthening of the polar vortex. And the plot here shows the solar wind anomalies from a nuclear war simulations with a different range of emission amount. And we can see that the larger strengthening of polar vortex with larger amount of aerosol emission, indicating those are the response to the aerosol emission. So to understand that, there has been a couple of theories to explain why that's the case. And this slide is provided by Ellen Robock, explaining the linkage between the aerosol and the climate responses. There are 4 mechanisms outlined here, but today I'm just going to cover stratospheric gradient mechanism and wave feedback mechanism. Those are 2 are more relevant with my result. So stratospheric gradient mechanism is simple. Whenever we inject the aerosol in the tropical or subtropical stratosphere, then it will warm the atmospheric layers there because of the absorbing shortwave radiation, but less over the polar latitude. And this differential heating will increase the meridional temperature gradient across the mid-latitude. And to maintain the thermal imbalance, the polar vortex should be strengthened following the temperature gradient. However, there has been some studies found that in their simulation, the radiative heating is confined largely to the tropics, not to the polar latitude. So the changes in temperature gradient is more pronounced over the subtropics, and the thermal wind is also pronounced over subtropics, as shown here, not over the polar vortex. But this westerly anomalies over subtropics means that it pushes the zero wind line, which is a waveguide for the planetary scale waves. So it induces the equatorward shift of the propagation of planetary waves, and less waves are breaking over the polar latitude, which in turn increase the strength of polar vortex in longer run. So with that, I'll briefly talk about the experimental design. I used the Wacom 4 with Karma, and for the emission protocol, I followed the Chuck Bardeen's India-Pakistan scenario. So I injected 5 teragram of black carbon and 1.6 teragram of organic carbon right into the upper troposphere. And then because of the black carbon's radiative effect, the smoke plume rapidly self-located to the stratosphere and spread over the stratosphere as shown here. And the plot on the left shows the temperature response from this India-Pakistan scenario. So you can see about 10 to 15 Kelvin of warming over the tropical and extratropical stratosphere. And we can also see the increase in meridional temperature gradient across the 60° north, because you can see large warming in mid-latitude, but less warming over the polar latitude. And the plot on the right shows the zonal wind anomalies, and the contours are the zonal wind changes estimated from thermal wind using the temperature anomalies. And those contours are similar to color shading, which is actual zonal wind changes, indicating that these wind anomalies are in thermal wind balance. That means if we can understand what is driving the temperature anomalies, then we can also get a sense of what is driving the zonal wind changes. So to understand the temperature changes, I looked at the heat budget of the stratospheric layers. Here, the plot on your left shows the temperature tendency calculated by the temperature field itself, and the plot on the right shows the temperature tendency estimated from this heat budget equation, which is basically some of all the terms in the right-hand side. And those two are broadly similar, indicating that this heat budget equation is accurately capturing the process contributing to these temperature anomalies. And I wanted to point out that the temperature tendency peaks around like first couple of weeks after the injection, and then within the time scale of several weeks, it actually decays to zero, indicating that the atmosphere is quickly adjusting to new equilibrium within a month. So to understand this, I simply differentiated the temperature tendency into two categories. One is the radiative term, which is just Q, and another is from dynamical processes, which is some of all other terms other than Q. And here, interestingly, the warming from the aerosol is actually largely confined to the tropical latitude, and the warming over the middle latitude is primarily driven by dynamical processes that are taking heat out of the tropics and transporting to the higher latitude. So our results are consistent with the stratospheric gradient mechanism, but this is driven by dynamical process, not by direct impact of radiation. So to further understand the dynamical tendency, I looked at the adiabatic temperature tendency from adiabatic process, which is basically vertical motion. So over the region that where the plume is rising, you can see the cooling and some warming over the adjacent area. But the warming in the extratropic is largely driven by the eddy heat flux convergence shown on your right, highlighting the role of atmospheric eddies inducing those temperature anomalies in higher latitude. And lastly, to understand the changes in polar vortex, I looked at the zonal momentum budget. And here we can see that the strengthening of polar vortex is largely from the eddy momentum flux convergence. And this is also consistent with previous studies, because whenever we have the thermal forcing in the tropics, we see there was more equatorial propagation of planetary waves, here shown as the EP flux vectors in gray vectors. And for another important term is the Coriolis torque, but those are the changes from Coriolis torque are largely confined to the subtropical latitude, and it does not affect much over the polar vortex. So I will try to conclude with highlighting what's new from our results among these different mechanisms. So I think the key result is the changes in these atmospheric eddies as a response to aerosol heating in the tropics is linking the local radiative effect in tropics to the circulation anomalies in the high latitude. So atmospheric eddies contribute to the increasing temperature gradient through the changing the eddy heat flux convergence. So it contributes to the stratospheric gradient mechanism, and it also contributes to the wave feedback mechanism by inducing the strengthening of polar vortex through wave inflow interaction by the eddy momentum flux convergence. Yes, with that, I will stop here and have to take any questions or comments.
And for questions?
So you said you see stronger ozone change because the polar vortex is stronger.
Yes, but also from the temperature warming, it increased the loss rate, and in the polar vortex, the positive feedback of stronger vortex, I think, contribute to the larger ozone loss.
A stronger polar vortex means colder temperatures inside the vortex.
Yeah, so here I think the temperature anomalies are warming is largely limited to the 60 degree north, and polar latitude is showing a little bit of
Okay. For temperature. Anyone else? Okay. Thank you, Shane. So we'll go to the final presentation of the afternoon. In the afternoon, Susan Bauer. Yes.
I'll share like this if it were.
Or you can be there, or
Super low resolution.
it takes a while.
Oh, it just takes a while? Okay.
Okay.
Oh, okay.
But I guess if I went over there, if I do. Let me go over there.
No, I just mean sit at the table. It's fine.
Whatever you like. Yeah, hi, my name's or up at the corner there. You could.
So many choices.
It's okay. I can also just stand. Hi, my name's Savannah Boa.
Oh, I understand what you want to do.
And yeah, I want to present to you AID-SAI, which is short for AI-driven emulation of SAI. It's a tool to disentangle and quantify uncertainties across spatial and temporal scales for stratospheric aerosol injection. And it's a collaborative effort led by Reflective, but with contributions from Cornell, Harvard, Scripps, and University of Wyoming. I'm sure most of you have heard of stratospheric aerosol injection, but just so we're on the same page, it's an idea to inject aerosols in the stratosphere to kind of mimic large volcanic eruptions, to lower temperatures, and yeah, some impacts of greenhouse gas driven climate change. And so unfortunately, currently, there are still large uncertainties around the chemistry feedback on stratospheric dynamics and the transport of tracers. Here I'm showing a plot by Simone Tilmes, where they look at 6 different GCMs and their temperature response to stratospheric aerosol injection. And what we can take from this is that for similar reductions in surface temperature, the stratospheric temperature change actually varies substantially. And so these sorts of uncertainties are a result of processes that happen at multiple spatial and temporal scales. So we have the microphysics, so aerosol nucleation, growth, size distribution. We have the turbulence in the wake of the airplane right after the injection. We have subgrid mixing, and then the large stratospheric circulation. And so what we want to do is build an emulator that couples these different scales. And with that, we hope that we can look at or explore these uncertainties faster and also more precisely, because we can disentangle them. And this tool, this coupled tool, is what we call AID-SAI. And it's supposed to be open source and not just for the SAI community, but also just to look at stratospheric circulation in general. So if you are interested in looking at some stratospheric dynamics, we're happy to, adapt or, make our tool useful to other communities and not just the SAI community. Yeah, a little bit more on the specific scales. So in the end, we want to couple all 4 scales, but for now we focus on where we started working on the largest and the smallest scales. So AID microphysics is the name of the emulator that emulates several microphysics box models, and AID Wacom is based on CSM Wacom. And yeah, AID Wacom is supposed to emulate the movement of tracers in the stratosphere. So we're not looking to build a perfect representation of CSM Wacom, but this is mostly to help us simulate the movement of the aerosols on the larger scale and to be much faster at that than CSM Wacom, so that we can build a large member ensemble And then, yeah, we're inspired obviously by the cannulator, but we're looking at higher altitudes and we focus on the movement of the tracers. And then AID Microphysics is looking at the chemistry and aerosol formation, and yeah, it tries to provide aerosol size distribution as accurate as possible while also being as fast as possible. And currently we're thinking of including Karma, Tomas, and Air3D. These are microphysics box models. And then in the end, we want to see all of these scales coupled, and this is what we call AID SAI. And we want to evaluate or validate the performance, obviously, and then use this to do uncertainty analysis for stratospheric processes. Stretch goal is we also want to couple it to an ocean to look at variables that are dependent on surface temperatures and do uncertainty analysis on this. Currently, we're still thinking about how exactly we want to couple. So here M is the microphysics scale, A is the atmospheric scale, R is a radiative transfer calculation, and then O is an ocean model. And so this is how we envision the fully coupled version to look like. So we have the atmospheric scale that provides the boundary conditions for the microphysics box model, and the microphysics output updates the aerosol fields in the atmospheric scale, but also gets fed into a radiative scheme that provides heating rates to the atmospheric scale for the next time step. So here's a little bit more of a more detailed view of that framework. So T0, T1, T2, these are the 8 Wacom time steps. And so in each time step, the atmospheric state gets calculated from the previous atmospheric state from external forcing, which for us is sea surface temperature, incoming solar radiation, and the aerosol tracer, so SO2, and updated aerosol fields from the previous time step and also the heating rates from previous time step. And so this new atmospheric state gets fed into the microphysics model, which feeds back into the next time step. And yeah, there's a couple of uncertainties that we want to look at with this, but we think that for a first pass, we maybe do not necessarily need the fully coupled version. So for example, to look at the aerosol spatial distribution, but then there are a few, for example, ocean uncertainties such as the AMOC or the carbon cycle, where we also want this to be coupled to an ocean. So these are longer term goals. And then we have another way that we want to quantify modeling uncertainties in the stratosphere in CSM Wacom, and this is by doing a PPE on the Pinatubo eruption. So we want to identify those parameters that lead to the best agreement with the observations, and also with that highlight which parameters are actually essential to look at for aerosols in the stratosphere. So we're varying 16 different parameters, and with that create 160 different combinations of parameters. And the parameters that we're thinking of looking at are related to the injection, to aerosol microphysics, and then to MAM, so the aerosol model that we're running these simulations with. And yeah, I want to say a few more words on the people that are involved. So I mentioned that this is an effort led by Reflective. Reflective is a nonprofit startup that focuses on SAI research. And yeah, our mission is to provide tools and resources to the community to facilitate the research. So one of our flagship tools is the SAI simulator, which is an emulator based on CSM Wacom, where you can explore surface impacts to SAI for different scenarios. It's very fun to play with, I recommend. And then we have this reflective cloud, which is a similar to GDEX, but focused on the SAI community. So we provide data and computing resources and community to people that want to be involved. Yeah, and so Aid SAI is supposed to be another tool in our toolbox that is focused on really looking at uncertainties in the stratosphere to SAI. And there's a couple of people involved, which I have listed below. And the ones in bold are the ones that are actually present here. So there's Hunter that looks at the Pinatubo PPE sitting over there. There is Ali that is the expert on microphysics. There's me working on 8 Wacom, and then there's Dan, who's the lead of the project, and so he's really the expert on all scales. And yeah, with that, I think we're all happy to take any questions that you have. And yeah.
Very nice presentation. So is there any question?
Yeah, I have a conceptual kind of question here. So once you analyze these model uncertainties, is the hope to then pinpoint what needs to be like the ideal state in the resulting model, or to get the best, the most accurate?
Your question related to the PPE now, or to the
related to, so you're saying you're analyzing uncertainties in SAI, right? So then you want, in the modeling framework, we want to reduce uncertainties. So would you be able to tell us, okay, so you need to focus on this part of the model to reduce the uncertainties, and this is the parameter space that you need to look at?
I think ideally, yes, because currently we see that there are large uncertainties, like I showed for the stratospheric temperature, but there are many parameters that impact that, and we want to really, reduce or constrain the number of variables that are relevant for this process. Mm-hmm. I would say that the main uncertainty we want to look at with this tool is the stratospheric transport feedback, where we really right now don't know how the specific small scale chemistry impacts, for example, the heating, and how that then impacts the large scale circulation. But others can maybe add to my response.
There are other questions.
Yeah, no, I think that answers the question.
But yeah, you answered perfectly. So
I have a question. I should take some time to see this slide in detail. But the previous one, where you proposed the complete scheme, or no, the one before that, shouldn't be there an arrow from radiation to the ocean?
Oh yeah, that.
If you go longer scales, or I don't know, what's the temporal frame or range that you would like to have this tool to work with?
Yeah, so you're right. I think we're mostly focused on, let's say, a couple of decades rather than a couple of centuries. But yes, we haven't thought about the ocean coupling that much yet, since this is such a stretch goal for us. Right now, we're mostly focusing on building the single scales and building the emulator for the single scales, and then to couple them. There should be an arrow from R to O. When I created this, it was there's not even an arrow from A to O right now, right? So this is more, the O is going to A, because this is the fixed SST that we're currently using as an input to the.
And there aren't actually any sort of machine learning frameworks, even Climulator. Not many have a coupled ocean. They're trying to have that, so we're probably not gonna break any ground there yet. But for now, we just hope to have coupled boxage for ocean memory. So in our case, it would only be there should be a double arrow between O and A, but for now, our A would impact. Our R would impact A, and that's it.
Then A.
And then A would go to the ocean.
Yeah. Okay. Okay. Really great to think on these things. Okay, any other question?
Very interesting into theme. I wonder, so the CSM itself has ocean scheme and radiative scheme, and what is the motivation for the OneChem is used together with the two feeding each other? Is it for safe vast computing resources, or what is the motivation behind the scene to do this simulator in this way?
So the reason why we're basing it on fixed SST right now, so excluding the ocean feedback, is because we wanted to have a really clean signal that we can train on. And because we're focused on stratospheric impact, the ocean is not that relevant for the impact that we want to look at. And also it just is faster to run. Yeah, I'd say that's my.
Just to add some color, I would say that I think this original idea came exactly a year ago in the last winter meeting when we were discussing. Essentially, if you just want to explore stratospheric uncertainties in WACAM, you can't decouple the processes easily, right? It's not like, you have CAM where you don't care about the stratosphere and just have CAM that is faster, but we don't have a WACAM with sort of fixed boundary conditions at the troposphere, and you can just look at the stratosphere, right? And so if you want to look at stuff like just sulfate uncertainty in the stratosphere, there isn't currently a way to just look at the stratosphere. You always have to keep everything fully coupled. And so our hope with this is to have a tool that is based and learns from WACAM, but then manages to decouple these uncertainties to explore them in a broader way.
So my understanding is that this motivation comes from apart from the machine learning perspective, but also you want to learn from this coupling thing by adding more physics inside of that by knowing which scheme contributing to the uncertainty. Thank you. Very nice talk. Thanks.
So thank you, Suzanne. I would like to thank all speakers on this afternoon session. We made it perfectly on time.
I think the presence of this, seeing the sun helps. Go to the other room where you just don't know what time is.
Discussion.
Yeah, so we have discussion time now. I have a couple of slides to show. We don't have to take all the time till 3 o'clock, but I can share some of these slides. And they're just a starting point for the discussion. So if you have ideas that you want to discuss that aren't on here, please add them. Okay. So I wanted to remind everybody that we're changing our name in the Chemistry Climate Working Group to the Chemistry Aerosol Working Group to better reflect what we work on in the group. So that's just going to be changed on all our web pages and all our communication going forward. We just wanted to remind everybody that's where we're going. This priority is a summary of what Simona showed on Monday. And so I just wanted to put this summary up here that we're really looking at adding the new forecast going forward, working on Musica V1 and V0 development and verification, so the spectral element and the NPAS grid development with regional refinement, improving OH representation by including VSL, methane emissions, and UVX. And then working towards CNIP 7 simulations, tier 1 and tier 3 developments in the model. So working towards CSM 3 and then doing those model simulations. Whoops. And then another few things regarding aerosols. So including nitrate aerosols, heterogeneous uptake on sea salt and dust, some solid aerosols, and including Karma as well. So these are kind of the priorities that Simone summarized, but there might be some more. Let me know if I've missed anything there.
Maria Del Martin is implementing online soil NO emissions. She's talked about them at these meetings for the past few years, but there are big pull requests going on. So hopefully that will get done. comments. So that's ready.
Anything else?
And another thing that the University of New Cardinal has a proposal to add ocean VOC emissions. So they're part of a big project that is making some measurements, or has made some, and so he's starting this summer, adding to the Oasis.
Okay.
VOCs.
VOCs. Yeah, I think what's missing on here too is the marine aerosols.
Okay.
Yeah.
That's another important.
And these are our outward facing web pages that I've linked here. The first one is priorities, which more have kind of a scientific focus, and the development plans are more like, these are the model levels. This is the like spectral element. So I just put those links there. So if you want to go and look at those, we can share. And there is overlap between those two pages as well, some overlap. Okay, and then these are kind of some points that we were thinking about, talking about. I wanted to remind people about the wiki page that we have that has information about the downward chemistry in it, if you want to learn to run it and do changes and what have you, and that's all on the wiki. And then we have a user page that has users and projects. And so if you are not on this page, then that would be awesome to submit your details for the Google form, and we can add you to this page. So this just has a whole bunch of people and what they're working on in the model. So yeah, and previous projects as well. So that's great to have a record of our community there.
I personally haven't contributed that much to any of these, and I think now that we have all these CSM2 SLH released and available for everyone, I'll take some time to add a tab on the SLH chemistry that I should have done it before, but that would be something useful for other users to have like a starting point or something like that. So I can work on that.
Yeah, so this is the wiki page here. So we could have a section down here on model component descriptions. We could have perhaps down here a VSL section.
I got really useful information from there, so also to provide some. Okay, yeah. I'll work on that. I'll take a note.
Really great.
And if anybody's browsing through this and finds anything out of date, let us know, or has recommendations for improving them. Just there's a lot here. I've come across things recently that it's like, oh right, this isn't the way it is anymore.
Great. And then we were talking earlier, and Nick reminded me that we wanted to do some testing between WACCM, the high top model, and the mid top model of CanCam. I should say CanCam, and trying to test both of those to determine when you would want to use WACCM versus CanCam CanCam mid top. So I don't know if you wanted to say anything else.
Just briefly, right? I think if anyone has ideas for shorter length simulations, especially, obviously we'll probably do some very long simulations where we can compare them. But if anyone has specific things that they think would be useful to look at, I think the question we want to make sure we can give guidance to people is, when can you use CAM mid-top to do stratosphere? This is more of a stratosphere question, when that's sufficient or when you should really use WACCM. Because I think, before that wasn't really a question, but now it is. And we don't want people to necessarily use WACCM because it's a lot more expensive if they could get away with the mid-top, but then We also don't want people to use the mid-top when you say, well, you should really be using Wacom because you're missing something because there's a deep enough sponge layer in the mid-top model. So some processes you might want are not being captured. So I think giving people guidance on that will be useful.
What's the timeline for these? You said the simulations.
I mean, I think it's a little bit of an open timeline. I think it would be maybe nice if by the summer, if CSM3 is being released, if we can at least have some initial sense of like, if you want to do SAI, should you use Wacom or mid-top count?
Kind of option.
Right, or volcanoes, things like that. I don't know if there's some volcano experiments you could run of like Wacom versus mid-top and easily just say like they basically produce the same thing or they don't, and then give at least some initial ideas to people.
The only thing I was thinking, sorry, the challenge is that for Wacom 7, there still isn't a fully coupled version with the ocean. So this would just be you're
okay. So it sounds like there was already a plan.
Well, it would be useful, we can.
But if anyone has other
future,
input.
We're meeting and get together and figure out a few more, for sure.
Yeah, I think a coupled version should be theoretically straightforward.
And it looked like Simone and Martina are already planning simulations, so people that want to get involved in that. If you can use a cheaper model to answer the question, it would be run past.
But we don't want people to misuse the cheaper model.
Right.
And I think, more in general, as we keep noting that, people keep using also older versions of Wacom. I think if there's, since with Martina, we've been talking about it since last year, read a paper that gives guidance to the community and also acknowledges people that are using Wacom 4 and, all of even just giving a better idea of like the improvements and why using a higher version, maybe there's still online TUV, that would be a huge change for a lot of studies. Definitely an important paper to have.
Okay, next on the list we have SIMF7 MIPS. This was a question that Nick brought up as well, and it was more about, are there MIPS that people want to be involved in specifically? Just getting an idea from the community. Are there specific MIPS that people would like?
It's obviously not. But I think this is something, Dave has been asking, what people would want to, what the different working groups want to participate in. And, I would like input from the people that are more involved, and maybe you are the most.
Well, but also so for this, I would note that it would be really important to figure out whether we actually are planning to use Wacom 7 per CB or not at all. I think and part of the question there is whether the mid-top is useful to the stratospheric stuff, right? Because which looks like up to now it is, and so it should be okay. So are we planning? I think we should discuss in these two working groups whether there's something that would be missing by not having Wacom 7 be in CMIP at all. Whether we want to do as we proposed back last year, right? Something like a restricted deck, like a small deck of simulations, or if we just want to figure out that the mid-top is useful, is the only thing that we're going to use. I think that's an important discussion to have. But in terms of the MIPS, of course, AirChain MIP is really important, right? And GeoMIP has a fast track experiment that would be great to run with the mid-top version.
I think these are all the different MIPS.
Yeah.
I don't know what these are.
I know. I sadly encouraged by the knowledge of all of that. So tomorrow at 9 in the morning Mountain Time, there's going to be the second session where there's going to be the carbon MIP, cloud forcing MIP, detection attribution MIP, GeoMIP, and the regional aerosol MIP. area MIP is the original aerosol MIP.
It's certainly input on what you think would be useful. I'm not
for these groups, yes.
entirely sure what the situation will be in terms of computing hours, and it probably depends on how expensive all of these would be. But if there's things that you think would be especially useful for the community, make sure that you provide the input. And if we can convince that it's really important, I think we can ask to use some of the allocation for those.
Or we can go as a community and, with university allocations cover the rest, right? But definitely the fast track experiments that are not all of these MIPS, but there are some specific key simulations that would be important to have, and those would be necessary to have them by the summer, given the deadlines for the working group on the VCC.
So just one comment related to MIPS. So they're not like fully coupled. That we with Doug and we've been participating in a MIP of DSL trends in the last 20 years, and also with some cyclical simulations to compute the stratospheric ozone depletion potentials of each of the main fluorinated halocarbons with Ryan Cosaini, Susan Termeyer, Doug, and some people. So Ilaria helped us with some files, because we needed to use, we decided to use the latest SLH version that we have, which is in CSM2, but then we needed to include all the same 7 emissions of ozone to be equivalent to the other models. So we have just run during the Christmas break and the next few weeks of most of those simulations. So like CSM 2.2 is being part of another MIP. It's not like a future climate projections, but it's so you are aware of it. Okay, we're working on that, and most of those simulations were already done. That's why we require for some additional time during the Christmas break.
So it sounds like we need to decide on WACM versus mid-top, or if we're going to use WACM at all in CMIP7. Is there a timeline on deciding on that? And how do we do that?
It's really internal, isn't it?
Yeah, I think it was from the discussions we had before. I think we won't run. Maybe we run 1 or 2 simulations just for comparison with CAM, and maybe it's also useful for some community that wants to look at the mesosphere. Having some data set of long runs to release to the community of WACM7, I think also serves some purpose. So to just say, well, we're going to do any long runs before we release it also is not useful. So we could maybe do some CMIP type runs and then just make them available, even if we're not really using them for CMIP.
Okay.
There is no timeline to upload stuff in our system grid. Sure, there's a fast track and there's stuff that if it gets done in the next year gets included in the working group 1, but whatever, right? Like even just for WACM 6 we did the same. Not everything was uploaded all at once. But yes, it would. I think it would be an incredible loss if WACM did not participate at all into the deck and some simulations, and then depending on how much time we have and how good the meetup is, we can select better.
Okay.
In regards to the model editor comparison projects, this isn't CMIP7, but AeroCom is discussing a perturb parameter ensemble model inter comparison, and I don't know if I'm not sure if anyone from NCAR is participating in that or has heard of it. No, okay. I'm not sure. Hiling, I think, but I can't remember exactly. I think it's still like kind of there are discussions about whether or not to commit to that, just because it's a higher computational commitment. But yeah, that's another option potentially for the national stage, and then participating with a lot of different modeling groups. It would be aerosol, and I think aerosol cloud interaction focused.
Yeah, that reminds me, we also have a wiki page on MIPS. So maybe once we have a clearer idea of what we are involved in, we can fill this in a little. So we could definitely put the VSL up here as well. And if we want to be involved in the ERICOM as well.
And I saw that, sorry, that list down, there's the track is the ISA MIP. Then it's down. I'm sorry, I thought it was, yeah, that one. And for this one, for which Ilaria did a lot of simulations, but the PP that Hunter is doing with Wacom is based off on one of the ISA MIP proposals, so we can add it there.
Okay,
Just say
yeah.
that we've done it anyway.
Yeah,
Yeah.
that'd be great. Anything else on MIPS? No? Okay, and then the final point that I have up here is what Rafa talked about this morning. Was it only this morning? About implementing SLH in CSM, and there were the 3 options. So.
So actually, now there are 2.
Oh, now there are 2?
Yeah, so B is not available, it's not going to work. I talked with Gustavo Marquez during the lunch break, and he said that's not going to be supported or not going to be implemented and maintained or anything in CSM3. So actually, I'm having a meeting with this tomorrow with Simon. Probably we'll have more updates on this. So what we think is might be useful not only for SLH but for other people like really familiar with CAM6 physics and all the developments that have been there to keep a couple model like it was in CSM2, but now with another ocean. So it could work on that. For sure, in the long road, the final stage will be for sure having SLH in CAM7, and we need to work on that on the Tier 2 point also. But in the meantime, maybe something to think about. I think I need to discuss with her, and perhaps Francis can also get in some specific details if this, how much this could take to have this done or not. I think it will require connections with other working groups, not only. For sure, this will be with the ocean. Gustavo also mentioned that we need to be sure also with CLM. It will only be the ocean, but also coupling between using CAM7 physics or CAM6 into this CSM3 framework is also the coupling with the LM that needs to be.
So it sounds like C would be a heavier lift than A, potentially.
Yes, I think it will. I know. I just learned about all of these incompatibilities a few days ago, so it's like trying to digest what's going to work on this.
Okay, and so maybe being available to the community quicker would be available through A.
No, actually, for the community, which is, I mean, if this is an issue of only SLH, it will be, don't use CSM3, use CSM 2.2. That's the release version, the published code, and in that you have the coupling with the POP, and everything is working there. So you can do that. So that part is solved. The thing is that like advancing now that we have all of this and any additional implementation that we want to keep track, or other groups working in improvements in aerosols or anything, won't be in the CSM2. Everybody is working on the Chem6 development version. So that's why we would like to have it there for prescribed simulations with the ocean. That will work. But it will be, I think, much demanding to have both of them in parallel to keep track of both of them. So it would be nice to have at some point. If we never reach that place to get point A, then yeah, for sure, point B, point C now, there should be done.
Any other comment?
Yeah, I think having the SLH in the, whatever the current version of the model is going forward is going to be important, because, from Ben's talk also, it has a big impact on the chemistry, and, we're just falling behind the rest of the community if we're not using this. So I think that's important to get it into Chem 7.
Yes.
Yeah, I mean, my initial thought would be to go for C if you hadn't like limited resources, because we want C eventually, right? That would be if we have limited resources, I would say.
Yeah, that's right.
But I don't know all of the ins and outs, so I think talking with Simone tomorrow. Okay. Is there anything else that anybody would like to discuss? Covered a lot. It's great. 20 minutes. All right. Well, thank you for a great session today. Great session. And we can be released 10 minutes early or 7 minutes early.
They said if anyone wants snacks or coffee, you're welcome to on the way out.